So welcome everybody to session 2 of CCC. This is the first session with an invited speaker, and the invited speaker is Thomas Vidick, a professor at Caltech. Currently, he just started his sabbatical in Paris. And Thomas is going to explain to us his recent breakthrough results about the just astounding power of multi-prover interactive quantum proofs. Go ahead, Thomas.
Thanks, Ronald. Thanks for the introduction. The sound is still okay? Yeah? Okay, cool. So hi, everyone. Thanks for joining. Let me thank the CCC Program Committee, and in particular Shubhangi, for inviting us to talk about our results. So this is a result that's obtained with Zhengfeng Ji, Anand Natarajan, John Wright, and Henry Yuan. And it's really nice to talk about this to this audience. I'm very happy that, very happy that due to the circumstances, maybe more people can tune into the talk than could otherwise. So the result that I'm going to talk about is a result that's indicated in the title. It's a purely complexity theoretic result, as might or might not be evident from the title. But it's a result that you can arrive at from different angles. And in fact, I've given versions of this talk to quantum information theorists before and to mathematicians, but never to complexity theorists. So of course, I had adapted the talk to the audience, but I'm still, so I'm going to talk about complexity theory. I still want to try to give you a flavor of the different angles using which you can look at this result and that motivated, because I think that's what makes it interesting. So the plan for the talk is that I want to first state the result, then I'll spend a little bit of time motivating it from different points of view, and then I hope that I have time to say a few slightly more concrete things about the proof or the interesting ingredients that go into the proof, though I will not have time to go very, very deep into it. Okay, so let's get started. Oops. Okay. So I'm talking to complexity theorists, so I think everyone knows about this, but you have to start somewhere. So the starting point is the class NP of languages that admit non-deterministic polynomial time decision procedures. An equivalent way to formulate this is that the language is in NP if and only if there exists a deterministic polynomial time verifier, so that's her at the bottom, such that when the verifier is provided as input an instance x, then she can determine whether the input is in the language or not by receiving a proof from Merlin. So this proof is provided by an all-powerful prover that is not in general to be trusted. So the requirement is that if the input is in the language, then there should exist a proof that this verifier accepts in polynomial time. And if the input is not in the language, then no proof should be accepted by the verifier. So this is a very rich class. One of the reasons that makes it so useful is that there's so many different natural complete problems for NP from all across computer science, but also from, you can find problems that are motivated by physics, biology, or other sciences. So starting in the mid-80s, different groups of researchers started considering different extensions of this notion of proof of efficient verification by introducing a couple of ingredients. One is a randomness, so we're going to allow the verifier to be randomized polynomial time, and the other is interaction. So there are different motivations for making these modifications. One of them is that it seemed they seemed to increase the class of languages that could be verified efficiently in this way. That was motivation by Babai and others. Then there's motivation from cryptography by Goldwasser, Micali, and Rakov, who realized that by allowing randomness in interaction, what could have special types of proofs that are called zero-knowledge proofs. And so they jointly introduced this class IP of languages that have verification procedures of this form. And a few years later, the power of IP was characterized to equal to p-space, so all languages that can be decided in polynomial space. So even though we don't know this for fact, we believe that p-space is bigger than NP, so it seems that these ingredients did increase the power of the class. Then just a few years later, another modification was considered. So that's the modification that consists of allowing the verifier to interact with two cooperating but non-communicating provers. So this modification doesn't change the power, doesn't increase the power of the provers, because the prover was all-powerful. Now there's two of them, they're all-powerful. In fact, it restricts their power because the verifier can now play some kind of, like, prisoners tricks kind of thing by asking questions to one prover and related questions to the other prover and checking that their answers correlate in the way that she expects. And so that gives her a little bit more power to verify the information that's coming for these provers. And in 91, Babaiford and Lund characterized the power of MIP. They showed that it's equal to nx, so non-deterministic exponential time. So now that is surprising because nx and np are strictly separated. So altogether, adding randomization, interaction, multiple provers increased the class of languages that can be verified efficiently. The verifier remains a randomized polynomial time procedure. One of the reasons that makes the MIP modification very rich is that, at least for the case of two prover, one round protocols, which you can show is without loss of generality, the whole verification procedure has you can reinterpret it as probabilistic checking of an exponentially long proof. So you can think of the list of all possible answers that these Merlins could each give to the verifier's possible questions as a very long proof. And the verifier, in order to make her decision, is only probing a couple locations in the proof. So there's one question to the first Merlin, another question to the other Merlin. And so this notion of probabilistically checkable proof that arose from the study of MIP then led to many results in complexity theory, including hardness of approximation, etc. So that's just background that most of you are familiar with, just motivation for the classes. Now for the talk, we're going to consider quantum modifications to interactive proofs. So there's two natural modifications that one can make. The first, maybe the most natural, is to increase slightly the power of the verifier by making her quantum. So this is a quantum computer that I gave her. And she can also exchange quantum information with the provers. So this clearly gives more power to the verifier. So the class is going to be at least as large as it was before and maybe a little bit larger. However, it turns out that in both cases, for single prover interactive proofs and multi-prover interactive proofs, making just these modifications, so quantum verifier and quantum communication does not change the power of the class. So it's a non-trivial result, especially the first result, QIP equal IP. That's very non-trivial. But in the end, the modification didn't change anything. It changes other things. So for example, with quantum communication, in the single prover case, all protocols can be parallelized to only 3 messages, and that's not known to be the case, or not believed to be the case classically. Okay, so let's unwind this modification because the classes are completely characterized. Let's look at, so I'm making the verifier classical randomized again. Oh, by the way, I just realized this is a bit late, but I think Ronald didn't quite say it. So if you want to interrupt me and ask questions, please do so. You can ask it in the chat and Ronald will pick it up and stop me, or you can just, I don't know if you can unmute yourself. So you can raise your hand and Ronald will unmute you. So don't hesitate to stop me if I'm not being clear. So I'm scaling back the verifier. Now it's again randomized polynomial time. And the modification that I make is I'm making the provers quantum. And in particular, I'm giving them an additional non-local resource. So in the classical case, we generally allow the provers to make use of shared randomness. And you can show that this doesn't make a difference, but you can allow it. In the quantum case, it's natural to allow them something called entanglement. I'm going to talk much more about entanglement soon, but in first approximation, you can just think of it as something that's very similar to shared randomness, but it's a little bit stronger. So the kind of correlations that they can get out of this new resource are slightly bigger. So this modification made the provers stronger. They have additional correlations. So this might make the class smaller because they can cheat, but it can also make it bigger because the verifier knows that they have this additional power. So maybe she can ask them to do other things. So our result is a complete characterization of this class of multi-prover interactive proof systems with a classical randomized polynomial time verifier and provers sharing quantum entanglement. That's what the star is for. And what we show is that this class is very big. So it's surprisingly big. It's equal to RE. That's the class of recursively enumerable languages. So that's all languages such that there's a Turing machine, such that when you give it an input in the language, the Turing machine eventually halts and says yes. And if the input is not in the language, there is no requirement. So a complete problem for RE is the halting problem. So it's really big. It contains non-decidable problems, the halting problem. It contains all decidable problems. So the result is surprising for multiple reasons. One of them I already highlighted, which is that we gave more power to the provers by making them quantum, but it turns out that in the end, this gives the verifier more possibilities for verifying broader languages. And maybe the most surprising fact of all is again that RE is just really big, right? So the halting problem is an undecidable problem, and here this verifier can, in a way, decide it, or at least verify it, by interacting with provers that are all powerful. So of course, the provers themselves can decide. It is assumed that the provers can decide the halting problem. So the goal for the talk is to explain the result. And the first thing that I have to do is to tell you a little bit more about this resource that I gave the provers and justify why I gave them such a resource. So that's talking about entanglement and the role that it plays in multi-prover interactive proof systems. So I have one slide of informal definition of entanglement. So it's really something that has nothing to do with complexity theory, nothing to do with interactive proofs. It's a physical phenomenon. You can think of entanglement as a state of matter. It's a state that a bunch of particles can be in. So these particles can be 2 photons, they can be 2 electrons. They could also be 2 cats if you believe Schrödinger. So it doesn't need to be a small particle. And these particles are said to be in an entangled state. If it is the case that when you make observations on, so separate observations on each of these particles, you obtain outcomes that are correlated in ways that you could not have obtained in a description based on using a description based on classical mechanics. And I'm going to make this a little bit more mathematical later. But the high level is just a state of matter such that when you make observations on the 2 systems, then the outcomes are correlated in ways that you don't expect. And I put the Wikipedia definition here in case you want to read it. It says something a little bit different than what I said. In particular, it says something I didn't say, which is that for these particles to be entangled, they need to have interacted in the past. So they interacted at a certain moment. At that moment, they entered a certain joint physical state, and then they got separated. And entanglement manifests itself even after they're separated. Okay, so the other thing that I want to say about this is that it's not, there's different theories in physics, and some of them, supersymmetry or something, they're just theories. So entanglement is a theory that's been verified many times by extremely precise experiments. This is a picture from one of the latest ones that took place where Ronald, or close to where Ronald is located, I'm assuming. So in the Netherlands. It's not only a microscopic phenomenon, so entanglement also plays a role in some macroscopic phenomena, all the way up to things that involve black holes. And it's also something that's, I'm not going to talk about this a lot, but it plays an important role in quantum cryptography. So you can do engineering based on, or you can engineer, entanglement and develop protocols and sell devices and build satellites that beam entanglement across different cities. Here, this is between China and Austria, just maybe 3 or 4 years ago. So it's something that's very real. And so it makes sense to consider the effect that it has in interactive proof systems, sort of from a complexity theoretic point of view, because it's playing around with the class and seeing how it's affected by small changes in the definition. And from a cryptographic point of view, and the motivation of MIP is cryptographic, then it entirely makes sense, because if you are to implement protocols with these distant provers, then for all you know, they could be sharing quantum entanglement. Okay, so let's get to it. So I want to make things a little bit more precise, starting with the classical case. So for purposes of the talk, I'm going to consider 2-prover, 1-round interactive proof systems. In both cases, it's without loss of generality, and it's also much simpler to explain. So in such a protocol, there's just 2 stages. In the first stage, the verifier selects a pair of questions according to some distribution, and each Merlin receives 1 question. Then the Merlins locally compute answers to their respective questions, forward them to the verifier, and then the verifier, based on all the data, so the instance, the questions she sent, the answers she got, her probabilistic polynomial time computer, makes a decision whether to accept the instance. So the way we model this in full generality is that the provers can be represented by a family of distributions. So for every pair of possible questions, so there's capital N possible questions per prover in my notation, then there's a certain distribution on pairs of outcomes that the provers can return. And different ways to model the provers, or different assumptions that we put on them, are going to lead to different classes of families of distributions over which we optimize the prover's success probability in the protocol. So in the classical setting, maybe the most natural setting, natural thing to say would be that each prover is supposed to perform a local computation. So let's give them the ability to use randomness. Then the first prover would be modeled by a distribution, Q sub A, such that for every X, this is a distribution on answers that the prover can give. And then there's Q sub B. And then the joint distribution is a product distribution. That definition is not very nice. In particular, it's not convex. So we typically allow them to use shared randomness. And so that changes the definition in this way, right? So don't be scared by the integral. This is just like an average over some distribution on shared random strings. Lambda is the random string. Mu is the distribution on it. Each prover gets the lambda, and then the first one also gets X, the other one gets Y, and then they have their own distribution according to which they give answers. And so that's the distribution. So that's how we model the provers in the classical two-prover one-round interactive proof. Here's an example of such a distribution. It's kind of a silly example, but it's just to give you an example. It's a bit boring, so you can stare at it. So this is the case where there's 2 questions, 2 answers. So for each of the 4 possible pair of questions, there's a distribution on answers. In all cases, you don't need to stare at this too much. In all cases, I put the same, so you can look at the first one. And this is just, it's a slightly biased distribution. It's biased towards, so cos squared pi by 8 is 85%. So it's slightly biased towards the provers giving the same answer. Okay, so basically they discard their questions and they use their shared randomness in order to give the same answer with probability 85% and different answers with probability 15%. Okay, so that's a strategy they could be implementing in the case where there's 2 questions and 2 answers. All right, so now that we modeled things precisely, I can briefly go over the Babai-Fortnau-Lund characterization of MIP as equal to NX. In fact, I'm really only going to talk about the upper bound because that's the easier part. So if you're given a language and that language is an MIP and you're trying to decide the language by other means, what do you do? So given an instance X, you know what the verifier does. This verifier asks questions according to a certain distribution, receives answers, and then she has a criterion for accepting. Your goal is to determine what is the prover's maximum success probability. The most naive way to do that is to enumerate over all strategies. So because the verifier is polynomial time, she can only send questions that are polynomially many bits long. So the total number of possible questions per prover is going to be some exponential. Same for the total number of answers, because that's as much as she has time to read. And so the set of all strategies that we need to enumerate over is a subset of exponential dimension space. And because of this shared randomness that I introduced, it's a convex subset, but it's also infinite. It has an interior. So we can't enumerate over all of them, but it's not an arbitrary convex set. In particular, it's a polytope, and it's a polytope that has exponentially many extreme points or vertices. These extreme points are given by the product distributions, so just without the shared randomness. There's exponentially many of those. And the verifier's acceptance probability in the protocol is, in general, if you write it out, it's a linear function of these probabilities. So in order to determine the maximum acceptance probability, you just have to optimize a linear function over a polytope that has exponentially many vertices. You can do this in non-deterministic exponential time just by guessing the best, the optimum strategy, the optimum vertex. So that gives you the inclusion. The lower bound is much harder. So the lower bound says that even though this might have sounded naive, in general, there's nothing better you can do. And, oh, I actually can see that someone raised their hand. Yeah, Celine.
Is it doubly exponentially many vertices?
Oh yeah, I'm sorry, doubly exponentially many vertices. Yeah. So, but right, thanks. So if you thank you. So if you enumerated naively over all vertices, it would take you doubly exponentially much time. But each vertex has a representation as an exponential size object. That's just a list of all possible answers for all possible questions. And so you can guess the optimal vertex in non-deterministic exponential time. Thanks. So that gives you an upper bound, and the lower bound. So the lower bound builds on a large set of impressive techniques that were first developed for the proof of IP equals P space, so encoding assignments in multilinear polynomials or low-degree polynomials, and then checking these assignments, and also the property of being a multilinear polynomials in using interaction. So I'm not going into that at all. The reason I put them up is that we won't really see it later, but extensions of these things like the multilinearity test, low-degree tests, probabilistic checking, extensions of these techniques play a key role in the proof of our result. Okay. So that's for the classical setting. Okay, so let's move to the quantum setting now. So I told you how to model classical provers. What happens for the quantum provers? So this is the same as it was before. And here's the key theorem that is implicit in what I said before. That theorem is a theorem from physics, and it's an actual theorem from physics, not like a physics theorem. So it's a mathematical theorem proved by a physicist that predates interactive proofs. It predates non-local games. It predates all that I've been talking about. Is from the 60s, and that theorem says that there exists families of joint distributions on outcomes for inputs that can, in principle, and we've seen and also experimentally, be generated locally. So these provers just, the Merlins just act locally, but do not have the form that's at the top of the slide here. So this doesn't capture everything that physics says is reasonable to expect can be generated by Merlins that are in space-time isolated locations. Here's an example. So this is a physical example. You can do an experiment where this is the statistics that you're going to collect. There's just one difference compared to the case before, is that in the case where both questions are 1, I flipped the probability. So instead of giving the same outcome with probability 85%, now you give the same outcome with probability 15% and different outcomes with probability 85%. One thing that you can observe about this distribution is that it has the property of being non-signaling. What non-signaling means is that there's no information in the first prover's answer about the second prover's question. In fact, if you compute the marginals here, in all 4 possible cases, the marginal is just uniform. Or you can, actually, I haven't given you enough information to make the marginal uniform, but you can set it up so that the marginal is uniform. So you just look at the outcomes of any one prover, it's just uniform, so there's absolutely no information about its input in there. So there's no communication.
There's a question in the chat from Massimo Laria. He says, should be 0, 1 on the top right. Is that a typo?
I'm sorry, thank you. I don't know if it was 0, 1 before, but yeah, it should be 0, 1 on the top right.
Okay,
so the 1, 1 is not doubled up. Thanks. So Bell's theorem, in fact, a refinement of it due to Clauser and some other field from a few years later, is that distribution that's there at the bottom does not have a form as a shared convex combination of product distributions. But it is a distribution that you can generate locally, assuming quantum mechanics. And so that's Bell's theorem, that such distributions exist. So this says that the modification of introducing entanglement is non-trivial. Something's going to happen. Like there's more things that the provers can do. What exactly is it that they can do? I'm not going to say this precisely. I put the math on the slide because some people like me like seeing the math, but it doesn't matter if you can't follow this. It's just to have something concrete. So in general, this entangled state that they share is represented by a density matrix. That's a positive semi-definite matrix that lives in a tensor product of 2 spaces, like each prover holds 1 space. You can think of this density matrix as a non-commutative generalization of the distribution mu on the shared randomness that we had before. And then instead of having a function of their question and their shared randomness, they have what's called a quantum measurement. So this is just a bunch of positive semi-definite matrices that sum to identity. There's a collection of such matrices for every question they could get. There's P's for the first Merlins, Q's for the other. And then there's a formula there, and you can check that this defines a well-defined distribution. It always satisfies the non-signaling principle. If all the matrices that I drew on the slide are diagonal in the same basis, so they all commute, you recover the previous formalism. But if you allow them not to commute, then you can cook up, for example, 2x2 matrices that are such that this expression is going to evaluate to the example that I had on the previous slide. Okay. So that's the formalism. And before, so I had a set curly C for the set of all collections of distributions that can be generated according to classical mechanics. Q is the quantum set. And so Bell's theorem is that the quantum set is strictly bigger than the classical set. And so that's the new set that we have to optimize over when we're trying to figure out what is the prover's maximum success probability in an MIP star protocol. Okay, so let's look into that. So that's the definition. So it's just exactly the same as the classical definition of MIP. The only thing I changed is I wrote quantum in front of prover. And by quantum, I mean are allowed to generate any kind of distribution of the form that I wrote on the previous slide. So that fits in this model of entanglement that's provided to us by quantum mechanics. Okay, so let's talk about the power of the class. So just a few observations. There's two ways to think about the modification that we made. I already mentioned this. One is that we're giving more power to the provers, right? And so they have a broader class of cheating strategies. And so the first day you're faced with that, you're asking, okay, like how much can it collapse? And so your baseline is going to be, well, if I talk to only one guy, then that's safe. And so the class definitely contains IP equals P space, because if you ignore one of the provers, then I didn't make any modification. Okay, but if I try to go a little bit beyond, so there's an interesting result that's due to Ito, and there's further refinements of it that says that if I was to give even more power to the provers, so not just quantum strategies, but what are called non-signaling strategies, so any family of distributions that respects the non-signaling protocol. There's also a class that's associated to that. It's a bit less motivated physically, but it makes sense because I'm still not allowing communication. It's called MIP with non-signaling resources. And it turns out that the optimum winning probability of the provers in such a protocol can be written as an exponential size linear program. And on top of that, it's the kind of linear program that can be solved efficiently in parallel. And so that gives you that class is equal to P space. So this is just to say that in some cases, if you go a little bit too far in how much power you give them, you can have a collapse to just the single prover class. For MIP star, together with Ito, a few years ago, we showed that collapse doesn't happen because we extended the Babai-Ford-Lund result to show that MIP star at least contains an exp. Okay, so in the other direction, you can say, well, can we go a little further? So let's try to use that these provers have entanglement to the verifier's advantage instead of just trying to prevent them from using it. And what sort of could push you in this direction is that if you try to show that it's fruitless, you're trying to prove upper bounds on the class. And there's no upper bound that's no non-trivial upper bound that's easy to show on this class. So the argument that I made before for MIP equals in NX involved saying that this set of classical strategies was a polytope with doubly exponentially many extreme points. The quantum strategies, they're also a convex set, and they live in the same dimensional space. So it's doubly exponential dimension, exponential dimension space. It's not a bigger space, and it's still convex, but it's not as nice. In particular, it's not a polytope. It has some round corners. And it's not obvious how you'd optimize over a non-nice convex set. In particular, if you go brute force, you have to enumerate over all possible strategies, but you have this problem of dimension. Like, do they use 1 qubit, 2 qubits, 3 qubits, 4 qubits? We don't have a theorem that says that fixing the size of the protocol, like some number of qubits should be enough. There is a non-trivial upper bound on MIP star that's due to work of Navasquez et al. And Doherty et al. From 2006. This shows that at least any language in MIP star, there's going to be an algorithm that terminates for yes instances. This algorithm is interesting. I'm not going to say what it is, but it's provided by a non-commutative extension of the sum of squares hierarchy. So that gives you a sequence of non-increasing upper bound on the success probability of the provers, and you can use that in order to show that MIP star is in RE. And so last year in Fox, there was a surprising result by two of my co-authors, Natarajan and Wright, and they proved the surprising result that the MIP star is a strictly bigger class than MIP. So they showed that it contains non-deterministic doubly exponential time. That was very surprising. In particular, to show the result, you must really invent a new protocol, right? Because if you think about the upper bound, if even the honest provers don't use entanglement to succeed, then you could enumerate over all non-entangled strategies and figure out if there's a good one or not in order to decide the language. So protocols for NEEX, they must ask even the honest guys to use a lot of entanglement. And that's a little bit surprising because you really have to invent truly new protocols. But they did this, and you can think of our result as a sort of like steroids version of their result. So I'm going to spend a little bit of time explaining it. Before going there, I wanted to make a little bit of an interlude. I'll try to keep this short because I know not everyone's interested. Now is a good time to make coffee or order lunch, or I don't know, it depends on your time zone, like open the beer. I just have a few slides. This is just sort of on the side, explain a little bit, because some of the importance of the result comes from connections to questions in operator algebras. And so I just want to review that a little bit. So it's mostly independent from what I said before. We'll get to the proof afterwards. This should just take 5 or 6 minutes. All right, so in order to explain the connection, I have to go back almost 100 years to the foundations of quantum mechanics, because these foundations are intimately tied to the development in mathematics of the theory of von Neumann algebras by von Neumann. So von Neumann Heisenberg introduced a particular formalism for quantum mechanics, the one that I had a few slides ago with the density matrix. And von Neumann sort of explored this formalism for itself. So he considered what are called von Neumann algebras, which I'm giving you the definition. So you can think of them as just sub-algebras of the algebras of matrices, except these matrices are allowed to be infinite dimensional. And they tend to be pretty wild objects. There's very few requirements on something to be a von Neumann algebra. It needs to be an algebra, meaning that you can add and multiply stuff. It needs to have a star, like a conjugate transpose operation. And then there's a very weak closure requirement. So it needs to be closed in the weakest way that you could think of. That's reasonable. And so this weak closure is what allows it to be pretty wild. And so this object having been introduced, an important task in math is going to be classify the different types of von Neumann algebras. And the classification that was initiated by Murray and von Neumann involves different types. These types, you can think of it as sort of how crazy the algebra is or how finite or infinite dimensional it is. So type 1 is basically just finite dimensional things. So type 1 is just matrix algebras, finite dimensional. Type 2, there are algebras that contain finite dimensional matrices, but also infinite dimensional. And type 3 is the wildest. It just only has infinite dimensional objects. There's no finite dimensional thing in it. Okay, so then they tried to classify this, and Alan Kohns got a Fields Medal for not even a full classification, but contributions to this classification, in particular type 3 factors. And as he was considering type 3 factors, in a paper that's now famous, he made an offhand remark that you can read. I'm not going to explain it. I'm going to explain a more concrete version of it. I'll say on the next slide why this remark became famous, but it's now known as Kohns embedding problem. Very roughly, this Kohns embedding problem says that if you take the algebras that are not the crazy ones, so not the type 3, then you should be able to approximate them arbitrarily well by finite dimensional things. So to make this concrete, let's look at the bottom of the slide. So this is a slightly stronger conjecture. It's the conjecture that all groups are hyperlinear. But it's kind of an analog of Kohns, even if it's a bit stronger for groups. And this would say that any group, so infinite groups even, so for any group, finitely presented group, there should exist, and any finite subset of the group and any precision, then you should be able to approximate the way elements multiply in an infinite set by matrices. Okay, so it says infinite groups. You should be able to realize the multiplication rule for over any finite subset and up to any precision by taking matrices of sufficiently large dimension. This is a strong conjecture. I don't think that people believe in it, but that much. But there's no example of a group where anyone can show that this property doesn't hold. And so this is still open. The conjecture at the bottom of the slide is an open conjecture. Okay, so back to Kohns embedding problem. One of the things that makes it important is the work of Kirchberg that took place like a couple of decades or 15 years later, that gave a reformulation of Kohns embedding problem in the language of C-star algebras. So this reformulation is surprising for two reasons. One is because C-star algebras are better behaved objects than von Neumann algebras in general. And the other is that this reformulation involves tensor products. So you can't understand the symbols if you don't know them already. But this is an equivalent formulation of Kahn's conjecture, and it asks if two different ways of putting a norm on tensor product of some infinite dimensional spaces are equivalent or not. So that conjecture, it turns out, is sort of a much more fruitful way to reformulate Kahn's embedding problems. There's many equivalent formulations of it in group theory, also in free probability, in many different areas. So this Kirchberg conjecture has become a very rich sort of focal point of a lot of research. There's a lot of papers that say, assuming the conjecture, this happens, not assuming it, this happens, it's equivalent to ABC. There's many equivalent formulations. And one of these equivalent formulations is to a problem in quantum information theory. So we're cycling back to what we were talking about before. In particular, it was shown by Fritz and Junger and collaborators that if Kahn's embedding problem is true or Kirchberg conjecture is true, then this convex set that I introduced earlier, so the set of quantum strategies, is could be wild, but it's not like absurdly wild in the sense that at least membership in that set is decidable. And if you know that membership of the set is decidable, then that's going to tell you also optimization over the set is going to be decidable, and MIP star is going to be decidable. So as a corollary of that result, you get that if Kahn's embedding problem or Kirchberg conjecture are true, then all languages in MIP star are decidable, because quantum strategies are not that wild, basically because of this equality between the two tensor products. I mean, I don't have time to explain that. So that's a corollary of their work, that a consequence of our result is that Kahn's embedding problem is false. So there should exist some kind of wild algebras, and also these two tensor products are not equal. So this is, one way I think of it is that in terms of complexity theory, our result is a characterization. It says MIP star equals RE, so it's sort of the end of the story in a certain way. From that point of view, this is why I like this angle. It's kind of an opening, right? It says that some interesting objects exist, and these interesting objects are hidden inside of our construction. They're not explicit, and so there's some amount of work into making them explicit and constructing these interesting algebras and groups and things like that. Okay, end of interlude. Back to complexity theory. So I think Ronald, I have like 15 minutes, maybe a bit less. Is that correct?
Between 15 and 20.
Okay, cool. So that's enough time to say just a few high-level things about the proof of the result. So here's a very high-level sketch. What are we trying to do? We're trying to show that any language in RE, and in particular the halting problem, that's a complete problem for the class, has a protocol. So we want a procedure that should be computable that takes as input a Turing machine, M, and based on the Turing machine, it gives a description of a verifier, or I call it a protocol. This verifier is supposed to interact with the quantum provers, and it should be the case that if the Turing machine halts, then the provers have a winning strategy, or at least 2/3 winning. And if the Turing machine does not halt, then they cannot win in the game. So we're going to do this in stages. I mean, at first I'm going to have a slightly weaker goal, and here's this weaker goal. So we're going to show the following by induction on integer k. K is going to be 0, 1, etc. We're going to show that there exists a polynomial time procedure V. Think of this as the verifier, except it takes two inputs. It takes the Turing machine M and also some integer n. N is not necessarily the size of the Turing machine. It's like some bound that you give it. And V is polynomial time in the length of the Turing machine M, and also this parameter n. And basically, this verifier is going to decide all languages that are in deterministic. I kind of dropped the non-determinism. It doesn't matter in the end. Tower of k exponential time, meaning as long as the Turing machine M halts in this 2 to the 2 to the 2, like k times steps, then there's going to be a winning strategy for the provers. And if it doesn't, then there isn't going to be. Okay. So if you prove this result for k, for some k, you've shown that tower of k exponential time is in MIP star, which is not okay. Then we'll talk about RE a little bit later. So we already know the result for k equals 1. For k equals 1, you're just sort of truncating your Turing machines at exponential time, and we already know that exponential time is in MIP star. That's the result with Ito. In fact, we know a bit more. We know non-deterministic exponential time. And the way we prove this result is by induction. We show what we call a compression theorem. This is the sort of the most surprising part of the result. It's a theorem that's going to say that if you can do this for k, you can do it for k plus 1. And the way we're going to do it is by taking a well, I'm going to show you on the next slide sort of the baby steps, which are a little bit easier to comprehend. So that's our goal. Let's do the baby steps. So the first step would be going from k equals 0 to 1. That's I'm kind of going to reprove or restate the results that MIP star contains an exp. One way to think about it is that we could have a starting point that's the definition of nexp. So nexp is exponentially scaled up version of np. So you can think of an exponential size verifier that is given input and exponentially sized proof and decides the language in this way. And what the BFL result does, and the quantum sound version, is that it transforms this exponential size verifier into a polynomial size verifier, which is able to decide the same language exponentially more efficiently by interacting with the two provers. So using a two-prover one-on protocol. Okay, so that's kind of compression. But it's compression in a it changes the nature of the object, right? I started from like a static verification, deterministic, and I ended with a randomized interactive protocol. Our goal is to do the same thing within the same model. So for example, one way to think about the double exp protocol by Natarajan and Wright is that your starting point would be you scale things up from the previous bullet. So you start with a naive protocol for n double exp. So that's a double exponentially sized circuit that takes the input and a double exponential size proof, and then it verifies it in double exponential time. And you can do a scaled up version of the previous result to get now an exponential size verifier. So these things, by the way, I'm cutting a few corners, right? To make this precise, there should be Turing machines, there should be implicit descriptions, etc. So if you're worried about that, like I apologize, it had to fit in the slides. So this is just an intuitive level. I would get an exponential size verifier that interacts with two provers. And the Natarajan Wright result, what they do is that you can do one more step. So you can get now a polynomial size verifier that interacts with two provers and that decides the same language in polynomial time. And what's surprising about this is that now the model didn't change, right? So what blew up exactly? Is exactly the same thing or what? So that's the starting point for our result. Staring at their way of doing this compression and asking, is it exactly the same thing? What blew up? And trying to figure out what blew up and then getting rid of it until nothing blows up, and you can iterate this procedure. So let me explain a little bit how you do the first step of this, and that's that this slide kind of has the main ingredients. Afterwards, I'm going to go a little fast. So let's think of your starting point as a protocol like this with the verifier and two provers, but it's an exponential time verifier when you start, and these provers are unbounded. So everything is exponential size because it's a protocol for n double exp. You want to make the verifier polysize. You want to reduce its size. Okay, so I'm going to call them like small verifier. That's the reduced size verifier, and the provers are just the provers in the original protocol. And what I do is I introduce some intermediate provers just as a way of thinking about it. And the small verifier is going to delegate the actions of the exponential time verifier to these small provers. That's our goal. Of course, in the end, we don't want 4 provers. We just want 2 of them. So what's really going to happen is that the verifier talks to just 2 provers that share entanglement. But the way we think about the construction is that each of the 2 provers should be split into like a small one that's going to interact with the verifier and also with the larger one. Again, so how does this work? There's sort of 2 ideas. The first idea is going to explain how the verifier delegates things with the small provers. So that also goes in 2 stages. The first stage is that we're going to use techniques from quantum information called self-testing to ensure that these provers have the right size. So they're trying to implement an exponential, they're supposed to be implementing an exponential size computation, like the original verifier. And we're going to control this by forcing them to share an exponential number of EPR pairs. And using quantum extensions of this multilinearity test that was invented in the Babai-Fortnau-Lund paper, we can do this using polynomial resources. So using polynomial resources, you can make sure that these provers have an exponential number of EPR pairs, and that's going to be kind of their workspace. Okay, so there's some interaction in order to make this happen. Now, what we want them to do is that we want them to create these exponentially large questions that are supposed to go to the big provers by making measurements on their qubits. And we want to control this. In particular, because the left provers are going to be bundled together and the right provers together, we want to make sure that they get exactly the right amount of correlation, right? Like life would be so much more easier if the BFL protocol had product distributions of questions, but it doesn't, and it's known that it couldn't. And so it's really important that the left and right parts get some amount of correlation, but not too much. And that's where quantum allows you to do something that you couldn't do classically. And the idea for this is based on the uncertainty principle. So here's how they're going to use their EPR pairs. So that's like 3 EPR pairs here. Like there's the 3 left halves and the 3 right halves. And there's 2 things we can ask the small Merlins to do on each EPR pair. They can measure it in one of 2 bases. That's what's different in quantum information. There's incompatible bases, the standard basis and the Hadamard basis, for example. And you can measure in the one or the other, but you can't measure in both of them simultaneously. That's the uncertainty principle. And EPR pairs are going to be such that if we tell them to measure their entanglement in the same basis, they're always going to get the same outcome. So for example, here they got 0. Again, same basis, but the other basis, like green, they got the same outcome, 1. But if we tell them to measure in different outcomes, then they're going to get uncorrelated bits. So the fact that they make certain measurements in certain bases is something that follows from the first bullet. So we have techniques to make sure that they do that. And now by leveraging the uncertainty principle, we can make sure that some fraction of the time they get the same outcomes, some fraction of the time they get uncorrelated outcomes. By itself, that's not super interesting, but you can push this further using technique quantum information to get partial correlation, kind of correlations you're interested in. In particular, you can set things up so that you make them get correlations that are exactly like the line point or point plane kind of distributions that underlie the low degree test. And that's really one of the key steps. Once you've achieved that, you've managed to force the small provers to locally generate the exponential size questions that the bigger verifier would have generated herself in the original protocol. You can assume they forward them to the big provers. Anyways, these guys are bundled together in the end. The big provers are going to be able to compute the best answers they could. We can't quite read these answers because they're also exponential time. But here we use pretty classical techniques to have these small provers prove to the verifier that the answers that they obtained satisfy the exponential size predicate from the original verifier. Okay. So that's how you get non-deterministic doubly exponential time in a nutshell. And the key part was really this use of entanglement, self-testing, and the uncertainty principle to force the provers to generate these exponential size distributions and check that they generate exactly the right amount of correlation between themselves, not too much and not too little. Okay, so that's k equals 1 or 2 or whatever it was, 2, I think. Now we have to scale it up. So then it becomes a bit, so I just have a picture because you're going to have something like this. And then there's going to be some other guys in the middle that are now double exponential large. And then they interact with the big guys and you repeat this any constant number of times. The really hard part, though, is to find, and that's what happens in our paper, is to find some kind of a normal form for these protocols such that you can iterate this. Right? So previous results didn't have a normal form. Right? The BFL protocol has a certain form. The Natarayanan right has a slightly more complicated form. And you have to look at that and look very carefully. What are the kind of distributions on questions that you need in order to implement these protocols? What are the distributions on questions that you need to test these distributions? And make sure that the two are the same, right? That nothing blew up in between. And so I think that's one of our contributions. In fact, it's even kind of an open question, like characterizing what kind of distributions have this form of quantum self-similarity in a way that you can use the distribution to test itself. So what we show is like some slight extension of the line point distribution has that property, but there could be other things. Okay, so if you manage to do this, then you've managed to show that MIP star contains non-deterministic, or let's say just deterministic exponential time for any finite tower of exponentials. That still doesn't give you RE. You have to take some kind of a limit to get RE. So we give a direct construction that you can think of as a fixed point kind of procedure. That's a little bit inspired of fixed point theorems about Turing machines that say that there is such a thing as a Turing machine that runs itself on its own code. So I just have this one slide to explain how this is done. So the high-level intuition is that we're going to design a verifier that behaves as follows. So the verifier is given as input, just as before, like a Turing machine, and a time parameter n. this verifier is going to run in polynomial time in the size of m and n. So what it's going to do is that it has time polynomial in n, so it can check at least that many steps. So it'll just run m for that many steps. And if m halts in that many steps, then we're done, or we don't even need the prover, so we just accept. If we're not done, then we need to enlist the provers. And we're going to ask the provers to prove to us that the compressed version of ourselves of exponential size would have accepted. Okay, so we tell them, well, look, like I don't have any more time. I did my n steps. Next thing I want to do is check m for 2 to the n steps. I don't know how to do this myself. I don't have enough time, but I have a Turing machine description of myself that would do this if I had exponential time. So please do this, right? And so you give that to the small provers, and they're going to do it in exponential time and then prove to you that it accepts, if it did accept. And if it didn't accept, they're going to spawn, some double exponential size provers and delegate it to these guys, and this just goes on forever. So why does this work? Just in 2 words. So if the Turing machine eventually halts, then at some point you don't need to create new provers. Like some of them are going to see that the computation halts, and they're going to prove all the way back down to you using PCP techniques that we halted at some point. But if the Turing machine doesn't halt, you need to continue creating these provers. And the definition of the model MIP star is that you're taking a supremum over all prover strategies, but each of these strategies has a finite dimensional entanglement. So you need to fix the amount of entanglement before you start the protocol. And so if the Turing machine doesn't halt, then you can show that the provers cannot win with probability bigger than half or some constant, because they're only going to be able to try to prove to you that the Turing machine terminates for some bounded amount of time that depends on their entanglement. Of course, this holds for any bound on the entanglement that they might be using, because the Turing machine doesn't halt. So there's nothing that's going to do the trick. Okay. So that's it. So let me summarize, and then I have a few open questions, and I have, okay, so I'll make the summary quick. So I told you about quantum multi-prover interactive proof systems with entanglement between the provers. There's 3 motivations for studying them. One is just like a purely complexity theoretic motivation. It's just changing the model a little bit and asking what happens, a little bit more power to the provers. Another is quantum information. So, entanglement is one of the basic building blocks of quantum information. We want to understand it. One way to understand it is by studying its correlations. They manifest themselves very strongly in this setting of interactive proofs. So it's sort of like a perfect match, and we want to study this. And then there's the connection with mathematics. It's a little bit more unexpected, which is very interesting. It's one of the things that make the result interesting. And so our result is just a characterization of this class, and the proof uses properties of entanglement. So the fact that you can force provers to share certain kind of entanglement, make certain measurements on it, and then combine with the uncertainty principle to force them to generate certain types of distributions in ways that are just not possible classically, because this result doesn't hold classically. Okay, because of my 3 motivations, I have 3 sets of open questions. Briefly, one that I'm just kind of curious about, because we characterize the class and our protocol only requires 2 provers. Sorry, this should be provers, not players. It implies that MIP star has a prover reduction theorem, just like MIP has. Having any constant or polynomial number of provers doesn't change the power of the class. But we don't know how to prove this result without proving MIP star equals RE in the first place. And so I think it would be nice to not have to do that. Another set of questions have to do with other modifications of MIP star. There's other modifications that are motivated by more mathematical questions or more exotic forms of quantum mechanics, like quantum field theory. And these could potentially verify languages beyond RE, or for example, co-RE, or things even above that. So that's an interesting set of questions. Quantum information, let me skip this. If someone wants to ask, I'll explain it, but I didn't really go so much into quantum information, so I'm not going to define everything. In mathematics, I think there's really interesting things to do, which are simplify our result, maybe get rid of Turing machines or something, and construct interesting algebras and groups. One of the natural targets is this conjecture about every group being hyperlinear. So because it's a little bit stronger than Kahn's conjecture, our result does not refute that conjecture. So it could still be that every group is hyperlinear, so has an approximation by finite dimensional matrix groups. It's a little bit more surprising now that we know that Kahn's is false, but I think that's an interesting direction for research, and I'll stop here.
Okay, thank you very much, Thomas. Good talk. So now we have about 5 minutes for questions. There's already 2 questions in the chat, so let me just read them to you, so you don't have to read the chat yourself. First question is by Massimo Lauria. Again, he says, what is the power needed for the provers? Is it sufficient that the provers are as powerful as RE itself?
Yeah, I think so. So that's a good question. So we actually do not have a, that's sort of an open question, like constructing from a mathematical point of view what this strategy is. So, but if the Turing machine halts in some bounded amount of time, then they don't need more than that amount of quantum time. So I think that probably shows that RE is enough. Yeah.
Okay, next question is by Yuval Filmus, a two-part question. Part one is, what happens if you limit the amount of entanglement? And part two is, your proof goes from n to 2 to the n. Can you simplify it by going, say, from n to 2n?
Yeah, thanks. So what happens if you limit the amount of entanglement, then, so the amount of entanglement that's required of the honest provers is, I think, like the minimum it could be. So our result definitely implies directly that if you limit the entanglement to f of n, then basically you can get protocols that decide languages in deterministic time f of n, or poly of f of n, or something like that. Maybe even non-deterministic time, poly of f of n. I think that would be reasonable, but that would have to be checked. And I think that's, aside from this distinction between deterministic and non-deterministic, that would be tight because, well, you can definitely put an upper bound of exponential in f of n, non-deterministic exponential of f of n. Okay, so I'm getting slightly lost in the parameters because I can't do this in my head, but the answer is we're going to have a pretty tight characterization up to deterministic versus non-deterministic, and maybe up to an exponential in the function f. If you're interested in this, there's a paper by Slofstra, Yuan, no, Slofstra, sorry, I forgot the authors. I think Slofstra is involved, maybe Yuan and Coudron, and they study questions related to that, but also in their case, the gap goes to 0, the completeness soundness gap. Okay, the other question is a question that I get a lot from the mathematicians, who are, why did you do n to the 2 to the n? Why not n to the n plus 1, right? Isn't that enough? Yeah, n to the n plus 1 would be enough. So if you could compress things that have, you'd have to be a bit more fine-grained into what you mean by compressing, but definitely 2n to n, that would give the result. It just so happens that the techniques that are used give for free, for all we know, 2 to the n to n. Could we make it simpler? Maybe, but I don't know how. So.
Okay, I see that Salil has raised his hand for a while. Salil, if you want to unmute yourself, you could just ask it yourself.
Oh, yeah. Thanks for the great talk, Thomas. Has anyone tried to translate the diagonalization argument that proves undecidability of the halting problem into the language of operator algebras or quantum information? Maybe this is getting at some of your questions here on the open problems.
Yeah, so yes, so in well, okay, I don't know the answer to your question directly. I know that this implication that our result refutes this conjecture. The way I originally learned of it is through this Kirchberg theorem, and it involves a bunch of theorems. It's not trivial. There's a simpler proof of just that implication by Isaac Goldbring and a co-author that's just that appeared after our result. That's almost entirely logic based. So there's a logic associated with von Neumann algebras, and you can study what models for that logic, and undecidability plays a role there. So that's a little bit explored. I don't think it's very explored. And yeah, so I can't answer the question directly. I don't really know more precisely than what I said.
Okay, Peter van der Boas has a question. Peter, unmute yourself.
Thank you. I'm puzzled about the requirement of having enough entanglement for making the construction work. It seems that at the beginning of the protocol, these provers generate just enough entanglement and then the process runs. But if that is an arbitrarily large number, and it should be, because you can basically have arbitrarily complex RE machines. It seems that you then must have access to some sort of random generator which generates an arbitrarily large number. And such a random generator in itself is an extremely powerful tool, because that basically is equivalent of introducing fairness in non-deterministic computation, and that brings the entire analytic hierarchy into perspective. So how do you plug that issue?
Yeah, so let me try a partial answer, and I don't know if I'm going to answer your question. So the definition of the class MIP star is pretty clear, and the definition is such that it should be the case that there exists a Turing machine such that for the verifier, whenever the input is in the language, then there should be a strategy for the provers that is accepted with probability close to 1, and if not, there shouldn't be. Okay, so there's a supremum hidden there. The winning probability of the provers is defined as the supremum over all quantum strategies for these provers of the probability of succeeding in the protocol. So that supremum is taken after you fix the language, after you fix the instance, right? So you fix an instance, you give it to the verifier, then you ask, is there a good strategy for the provers? At that point, you take a supremum over all possible quantum strategies. And that supremum is a supremum over all possible amount of entanglement that they could generate. So you're definitely not required to have like a uniform model for the provers where themselves they have some kind of machines that generate as much entanglement as they need after the instance is revealed to them. You only need for it to be the case that once you fix the instance, there's a strategy for the provers. And so that, that as long as the Turing machine halts, there's going to be a bound on its halting time, and then there's going to be, when you take the supremum, you're going to allow yourself to consider enough entanglement for the provers. So I think this is it's the standard definition of the interactive proof classes, the place where we put the supremum.
Okay, the time slot.
If this helped. Okay.
Over, but I see one more question in the chat, so maybe we can do that quickly too. If people want to take a break, of course, you can take a break. So the last question I see is from Daniel Dadouche. He asks, where does the fixed point view come into play? Do the strategies for higher and higher running times somehow converge to a fixed strategy?
Yeah, so well, no, so there's many interpretations of the question, maybe, but one open question that's related to your question is construct explicitly what is the winning strategy for the provers. What is the optimal strategy for them? And we show that it exists by some induction, but I don't know how to construct it explicitly. So the fixed point theorem gives you existence of the verifier. And then by analyzing properties of that fixed point, you can show that there exists a strategy for the provers exactly when there should be. But you don't end up constructing it. Constructing it is a step that needs to be made in order to get a handle on these interesting objects, because they have to do with the prover strategy rather than with the protocol.
Okay, maybe I can take the privilege to ask one last question. And that is, so how essential is the quantum entanglement? I got the impression from another talk about the same paper that somehow effectively you just want certified randomness. Is that right? That the entanglement is certified, and at that point there's sort of randomness, and you know that the two provers have good faith randomness. Is there something similar you could do with a classical model where you somehow force the two provers to have like good faith randomness? Yeah,
that's interesting. So maybe you can do that. So introduce, a model, think of this as a model that kind of extends the shared randomness model where there'd be some buttons or something that you can do to the provers that, the quantum model in a way is that, because in the end, it's just distributions, right? So you can forget about entanglement. The quantum model is just saying what are the kind of distributions that these provers can do, and it's a bit more than the classical distributions. It's a bit less than the full thing, and that's what's interesting in it. So I think maybe something interesting behind your question is can we in a way clean this up, right? So in light of our results, find some natural class of probabilistic strategies, correlated probabilistic strategies, that is just the right amount of a extended power compared to straight randomness, but also limited power to enable this kind of verification capability that the result has. I don't know about that. It would be good to simplify the proof and clean things up. Yeah, that's a possible way to think about it. Thanks.
Good. Okay. Thanks a lot, Thomas.
Thanks everyone. Thanks for showing up.